Professor Menes to explain radiation. Please.
Okay, thank you. So I'm sure everybody knows the radiation of cichlids in this audience. It's one of the most impressive radiation, with, for example, more than 500 cichlid species in Lake Victoria, and we think that these species appeared in less than 15,000 years. And these species are reproductively isolated by mate choice, and associative mating is based on the colors of individuals. So the landscape of the Great African Lakes consists of several large lakes surrounded by many smaller lakes. And we know that there are several habitat types in these lakes, such as pelagic, estuary, or rocky habitats. And we also know that there has been climatic fluctuations inducing water level fluctuations, and this has resulted in the repetitive fragmentation and fusion of lakes. So in other words, the population in these lakes have oscillated between allopatric and sympatric states, a phenomenon that I called landscape dynamics. So there are mainly two scenarios to explain the radiation of cichlids in the Great African Lakes. The oldest says that each species is a result of an adaptation to a specific habitat. However, this scenario seems to be unlikely, given that it's difficult to imagine enough differentiated habitat to explain the huge diversity in these lakes. Another scenario says that evolutionary branching occurs repetitively in sympatry. However, this scenario remains controversial, in particular because sympatric speciation may require rather specific conditions, such as, for example, few loci determining phenotypic traits, so that the effect of recombination can be balanced by the effect of disruptive selection. And in both scenarios, the effect of the landscape dynamics of the Great African Lake is neglected. So I ask the question, could the landscape dynamics of the Great African Lake, defined as the repetitive alternation between allopatric and sympatric states, explain radiation? To answer to this question, I use the following model. So I assume that individuals are in competition for resources, and we have an implicit distribution of these resources with a maximum corresponding to an ecological optimum. We record the evolution of two phenotypic traits, a bidimensional ecological trait, X1, X2, and a mating trait, A, with associative mating based on a one allele mechanism. We chose the parameters of the model such that the fitness landscape hold an evolutionary branching point at the ecological optimum of the resource distribution. So we expect that the population converge to this strategy, and then selection is disruptive, and the population can split into branches of differentiated individuals. However, we assume that the population, this is a sexual population with polygenic inheritance. We assume 8 loci for each phenotypic trait, and because of this genetic constraint, evolutionary branching is rare with this model. So the landscape in the model consists of one central site surrounded by 5 satellite sites, and we assume that there is only 3 habitat types in all these sites. So 3 habitat types defined by 3 different distributions of resources. The landscape dynamics of the model is the stochastic fusion of neighbor sites, and the merged sites can be fragmented again stochastically. In merged sites, individuals can have access to all resources of the merged sites, and we assume that there is only one ecological optimum even in merged sites. Okay, so the question is a radiation expected given these assumptions? The answer is no, because according to the adaptation scenario of the radiation, we have only 3 habitat types, so we should have only 3 species. Because of the genetic constraints, we measured that we can have only 3 to 4 species generated by evolutionary branching in St. Patrick. So a radiation without considering the landscape dynamics mechanism, a radiation shouldn't be possible. As you can see on these typical simulations, with the landscape dynamics mechanism, we can generate a high diversity, up to 30 species. So the question is why? These 2 graphs show each individual by a dot here in 2 allopatric sites isolated from the 4 other allopatric sites of the metapopulation. And we have 2 different habitats in these 2 allopatric sites, with an habitat E here, with an ecological optimum here, and the ecological optimum of the habitat R is here. So I remind that the 2 axes, x1, x2, are the 2 components of the ecological trait. So the first step of the diversification mechanism is allopatric divergence in each of the allopatric sites. Then each species is on its ecological optimum, which is an evolutionary branching point, so that assortative mating increases, but without evolutionary branching because of the genetic constraint. And after some time, individuals from this allopatric site and this allopatric site are reproductively isolated by mate choice, so we have 2 species. Then the 2 sites merge, and we now have the 2 species in the same 2 merged sites. And if reproductive isolation is not perfect at the time of secondary contact, we can have reinforcement, because the 2 populations evolve under disruptive selection, so hybrids are selected against, and reinforcement stops the production of hybrids. Possibly, we can, if the 2 species at the time of secondary contact are ecologically close, we can also have a character displacement occurring. Then the 2 merged sites become fragmented again, and we now have the 2 species in the 2 allopatric sites. Allopatric divergence occurs again. Allopatric divergence to the ecological optimum of each site. And because of competitive interaction between the 2 species, none of the species is on the ecological optimum of this site, and of this site also, of course. So we have now 4 different species because of this mechanism. So we can imagine what will happen if we repeat this sequence of allopatric divergence and secondary contact and allopatris secondary contact. We can have many species in each site. So this mechanism explains why we have a radiation, but this does not explain why sometimes diversity is very high, where sometimes it's limited. It does not explain the speed of increase of diversity, which can be very different depending on these simulations, and also the stability of the level of diversity. In fact, all these characteristics of the radiation are determined by the characteristic timescales of the landscape dynamics. So I will illustrate this with one example, the blue time series. So for this one, we have a very high diversity, but we can lose almost all diversity very rapidly. And this kind of radiation is generated by fast landscape dynamics in a landscape mainly fragmented, which means that sites are most of the time allopatric, but we have frequent and short secondary contacts. So in this case, because we have significantly long allopatric states, we have a significant allopatric divergence. And because we have frequent secondary contact, the diversity generated in allopatry can be often propagated into sympatry, so that the main diversification mechanism I just showed you is very efficient. Second, because sites are most of the time allopatric, we can have different spaces with very, very weak ecological differentiation in allopatric sites, because these spaces do not compete with each other. So for example, in these two sites, we have the same habitat, but we have only two species which are identical between the two sites. So we can have a lot of diversity because of that. And what can happen if the two sites like that merge? One possible outcome is the loss of reproductive isolation between two species, and in that case, the phenotypic variance of the population increases, so that other populations, other species begin to hybridize with the hybridizing populations until they merge into a huge hybrid swarm. So we have now only one species. We have lost almost all diversity. Of course, because the phenotypic variance is very important, we can have evolutionary branching, recreating some diversity despite the genetics constraint we have assumed. So this explains why we can lose diversity. So to conclude, this model shows that landscape dynamics is a mechanism which can possibly generate a radiation even under conditions known to impede a radiation in a static landscape. And this is because of the joint action of different evolutionary mechanisms specific to different geographic background, in particular allopatric divergence and reinforcement and character displacement in sympatry. And these evolutionary mechanisms are repeated in different combinations at each landscape change, so that diversity can increase at each landscape change. And the features of the radiation mainly depend on the characteristic timescales. And just in 1 second, I would like to stress the importance of considering landscape dynamics in models of evolution, because all landscapes are dynamics at a given time scale and a given space scale, and this is usually ignored by formal model, but their effect can be critical, especially when landscape dynamics are fast, because in this case, evolutionary equilibrium, which are usually assumed by models, are not reached. Yeah. Thank you.
Are there any questions?
Yeah, that's quite nice. I have, the main question I have is, why so fast? This explains an overall pattern, but how is it that the fish speciate so rapidly? come to conclusion? And the second part of the question is it possible to combine the landscape dynamics with the second hypothesis that you showed at the beginning?
Yes.
To get that to happen?
Okay, so the answer is in your question, because with only the landscape dynamics hypothesis, it's relatively long to get many spaces, and it can't explain why the cyclid speciate it's impossible. However, if you have also evolutionary branching possible at the same time, you can have diversification in allopatry, but also in sympatry. And if you have also secondary contact, all diversity can be propagated to other sites. Whether this diversity has been generated in allopatry or in sympatry, it doesn't matter. And in this case, the radiation is very fast. I didn't show it here because I want to stress the importance of landscape dynamics, but yes, I think it's the reason. It could explain that.
Thank you.
Are there more questions? If not, then let's thank Robin